Well, welcome to another fun-filled day of physics. Today we're going to continue talking about interference. I introduced you to the idea of thin film interference, but we'll do some examples and we'll see kind of how that plays out, remembering the interference comes from two things. One is the potential phase difference due to reflection, and then the other is the distance actually traveled by the wave, the extra distance that was traveled, kind of like we saw with the two-slit interference. So we'll talk about that, and then depending on how time goes, we might get into what's called diffraction, which is really interference, but it's interference from a different sort of, or for a different reason, which is why we call it something separate. So anyway, but before I get into that, any questions about the homeworks? Because the homework chapter 2 is due tonight, and homework chapter 3, I'll have that up in tonight, so you guys can start working on it. But any questions on the homework? All right, well, hearing none and seeing none, I'm going to go ahead and bounce up to the whiteboard, and let's keep talking about thin film interference. All right, so I'll be right back with you. All right, so last time we've been talking a little bit about interference, and we saw that interference can happen a couple of ways. Excuse me, but really where we're getting interference, it's because our waves are such that they're overlapping with each other, and so we're getting constructive and destructive interference. In terms of light, constructive means bright, destructive means dark. And so like with that two-slit experiment, when you guys did that in the lab, you saw the alternating light and dark bands. Well, that's due to interference. But the same thing happens with thin films. And so just to kind of remind you what we saw there, suppose that this is a thin film of something, water, oil, ice, you name it. But what's going to happen is the light comes in here. It's going to reflect off of the surface. Some of it is going to pass through and then reflect on the other surface and then comes back out. And so it's these two rays that are interfering with each other. Okay, and so what we saw is that we actually have two things that we have to take into account in terms of the interference. One is the extra distance traveled. And the extra distance is going to be 2 times the thickness of this layer. Now, it's not exactly 2 times the thickness because of the angle here, but if that ray is coming in mostly vertical, this offset isn't as much as what I've drawn. I'm exaggerating it in here so you can see it, but in reality, that spread would be pretty minor. And so the actual extra distance would be like 2 times that thickness. So that's sort of like with the double slit experiment, right? Where the one ray had to go an extra little bit. This is that extra little bit. But the other thing that we have to worry about are the potential phase changes due to reflection. And this is all about the n values. All right, so if n1 is greater than n2, there's no change. So if we're going from a bigger index of refraction to a smaller one, there is no change. But if n1 is less than n2, then it goes out by half a wavelength. So we need to keep that in mind as well when we look at, do we have convergence or divergence, right? Do we have constructive or destructive, I should say, interference? Okay, and then the last sort of bomb I dropped on you at the very end of class last time was that the wavelength actually changes in the material. And so I'm going to do this in a slightly different, in a different color on the board, just to draw your attention to it. But it turns out that the wavelength is different in the medium. And in fact, we know that the wavelength in the medium, so I'm going to call it y sub n, or lambda sub n, is equal to lambda divided by n. And I showed you where that came from, just from the wavelength, frequency, speed kind of deal. All right, so since the speed changes, but the frequency doesn't, because it has to, the wave fronts don't start like piling up as we're going into the next medium, that forces this. So this is going to be the thing that you forget the most, because you're going to come in here and you're going to go, oh, okay, so that 2 distance, the 2 times the thickness, that needs to be a whole number of wavelengths. So you cycle the wavelength in a vacuum or air, and then you find out, oh crap, that doesn't work because this is actually oil or water or soap, or right. So we need to make sure that we adjust for that and go. So let me show you an example. It's not really that hard. It's just we got to pay attention to these 3 things. We got to keep those in mind when we do this calculation. All right, so here's an example.
I have a quick question for you.
Yeah, go for it.
Does lambda return back to its original state once it exits the medium?
Absolutely. Okay. Yep. Because now, like, let's say this was air to soap, right? We're talking about a soap bubble, let's say. So it's in air, so its n is 1. And then it comes in here and the n is, let's say 1.5 or something, right? So it slows down. But then when it comes back out into the air, it speeds back up. And so since that change in velocity happens with the same frequency, it ends up changing its wavelength back to normal. Yep. So, I mean, here's the other fun thing to think about this one. You think about this, the fact that the wavelength is different. Suppose that you were in water, right? So you're just in water. When you see something that looks, say, yellow in water, it wouldn't be yellow in air. If you take that, if you were to see those same wavelengths out in the air, it would be a different color. Have you noticed that?
Yeah, for sure. Like when you pull a rock out of the water, it looks different than it did when it was in the water.
Yep. Right. And the same thing, like if you're in water and you're like looking up, let's say, you're in the lake swimming, you're underwater and you look up at stuff, so the trees and all that, they have a slightly different color because of this fact. Right. So kind of another interesting, weird thing that we experience, that we see, but you may not think about why, but now you can see why. All right, so let's do this. Let's suppose that what we're going to do, we're going to put an anti-reflective coating on a lens, on a piece of glass. All right, I know that a lot of glasses have them, like mine actually have an anti-reflective coating. And so let's say that here's our situation. So we're going to have glass. And on top of that glass, we're going to have a thin layer and this thin layer, we're going to use magnesium fluoride. It doesn't really matter what it is, but magnesium fluoride is one of the things that is used for this. Okay, so let's think about what happens with the rays that come in. So we got the ray that's coming in. It's going to reflect off the surface of the magnesium fluoride. Some of that is going to come down, hit the glass, and then reflect. And there will be a third one, right? It'll also pass through this glass and reflect and then come back out. But we're going to ignore that one because it's going to be pretty light. It's pretty small intensity by the time we get there, right? Like you think about my eyeglasses, the great majority of the light is just going to pass on through anyway. And each one of those reflections is going to get dimmer. So by the time we get past that second reflection, the third reflection is going to be pretty much. Okay. So we're just going to ignore that one. We're just going to look at these two. Now, here's what our goal is going to be. Our goal is we want to cancel the middle of the visible spectrum. All right. And so that's going to be somewhere around 550 nanometers. Right? Plus or minus. The reds tend to get into the high 6s. The purples are down around 400. So that's kind of in the middle. So that's kind of a greenish kind of color. All right. So the idea is that if we make it so that we are destructively interfering kind of the greens, and we know that as you kind of move on the spectrum, it's going to get a little bit more on each side. Well, this is going to target most of visible spectrum. All right, so that's our goal. We want to cancel out the wavelengths that are around 550 nanometers. So here's my question, is how thick should it be? How thick of a layer of that magnesium fluoride should be on the glass to cancel out 550 nanometers? Okay, so here's kind of your typical one of these kind of problems. So there is one thing though that we definitely need that I haven't given you. And what is that? What important information is missing from this?
The end values for magnesium fluoride and the glass.
Yeah, we definitely need to know the end values, right? Without the end values, two things happen. One, we don't know about the reflections. I mean, it's a good bet. It's a good bet that magnesium fluoride has a bigger end than air, right? So that one we can probably assume. So we know what's going to happen at that reflection, but we don't know what's going to happen at the second one. So that's the first thing that's an issue if we don't know N. And the second thing that's an issue is this. We don't know what the wavelengths of that light are in the magnesium fluoride, so that we can set our thickness equal to either the whole number of wavelengths or a half, depending upon how everything plays out. Okay, so I still got to give you some ends. I don't know if you guys have picked this up for glass yet. Glass, we tend to use 1.52. That's a pretty standard N for this one. So we'll go with this N is 1.52. And then magnesium fluoride, it's going to have an N of 1.38. And air, we'll just go ahead and say has N equal 1, even though it's not exactly 1, it's close enough. And if we are going to round to 2 decimal places like these, it would still be 1. Okay, so now we actually have enough. So here's the first thing we should do. We should think about what happens when we reflect. What kind of phase difference are we going to get due to the reflection at those two surfaces? So starting with the air to magnesium fluoride, we're going from smaller to bigger N. So from smaller to bigger means that it's going to immediately get 1/2 of a wavelength out of phase. So what I do is I just write above this lambda over 2 That's my shorthand for remembering, there was a half a wavelength swap. So that reflection, it gets out of phase by half a wave. All right, so what about the other reflection? The one from going from magnesium fluoride to glass? What kind of phase change are we going to get there?
The same.
Yeah, exactly the same, because we're still going from smaller to bigger n. So that's also off by half a wavelength. So basically, here's the way to think about it. The reflections don't do anything in terms of constructive or destructive. So the only thing that's going to matter then is that extra distance. Okay, the extra distance is going to be what causes the destructive interference. Okay, so let's think about what we're trying to do. We're trying to cancel out the 550 nanometers. So that means that we need the thickness times 2 to be half a wavelength, 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths, and so on. So I'm going to put here m plus 1/2 times lambda. But that lambda is actually lambda n. So I need the wavelengths in the material to be such that when it goes down and back, so to the thicknesses, that it's either a half a wavelength or 1.5 or 2.5 or 3.5 or 4.5, and so on down the line.
What does M represent?
M is just a counting number.
Okay.
0, 1, 2, 3, 4, 5, 6, 7.
Okay.
Right? Because the thickness, I mean, it could be half of a wavelength, or it could be 1.5 wavelengths, or 2.5, or 3.5, or 4.5. So okay, in math class, we would have used n for that. Right? Like think about when we write, say, plus 2 pi n. But we're not using n for that here because n is reserved for the index of refraction. Okay, so well, let's see. Let's put in our lambda n. Let's change that to the original lambda over n. So we get 2t equals m plus 1/2 times lambda over 1.38. So our thickness is going to be m plus 1/2 times lambda over 2.76. And that lambda is the lambda that we're trying to cancel out. So we'll put that 550 in there. So 550 divided by 2.76. And that's awfully close to 200. Right? 2.75 into 550 would give us 200. So I'm just going to round it to 200 just to make life easy for us. So we're going to get t is equal to 200m plus 100. And the units here are nanometers. Yeah, it's not exactly 200, but I don't have a calculator on. Okay, so the question is, how thick should it be? Well, we have some options. We can let m equal 0, and that would give us 100 nanometers. So if it was 100 nanometers thick, it's going to cancel out into the greenish part of the spectrum completely. And then the parts around the green, so the yellows and the blues, and then a little bit more of the oranges and indigo, right? Those are going to get canceled as well. But that's 100 nanometers. Or if M is 1, we could have 300 nanometers or 500 nanometers or 700 nanometers or follow that pattern. So that's what this M is doing, is just saying, well, you can let that be any counting number you want, and that will give you a thickness that does this. So it's not just one thickness that will make this happen. There is a smallest thickness, 100 nanometers. That makes it so that there was exactly 1/2 wavelength as we went down and back. But we can have 1.5 or 2.5 or 3.5, excuse me, and so on. All right, so kind of making sense? Do you at least see what we have to watch for? Things we have to take into account?
I'm just curious as to like, do these other values for thickness dictate what other things will be taken out of the wavelength as well? Like, that'll also be destructive interference?
Yes, absolutely. When we do this and we talk about it being like a thin, it's like we call it a thin film, right? The thin filmness makes it so that we're only losing that one wavelength. Because if it gets thicker, right? If we start getting to bigger ones, what we might find out is that now there are other colors that are being constructively interfered. So it's not, we're only canceling out the greens, but we're making the purples really bright. And sometimes that does happen. Like, I don't know if anybody actually has camera lenses and has looked at those things that have those filters, but if you look at them, they kind of look sort of pinkish. I know even my glasses sometimes will do that. If you look at them just right, there's sort of like a pinkish purplish hue to them. And that's because the thickness is such that it's actually constructively interfering those colors. So if you make it really thick, like if we go down and we let M equal, 100. So we've got, what would that be? 20,100 nanometers. So what was that, 0.2 millimeters or something like that? Okay, so you get really thick. Well, yeah, now all of a sudden we have issues with some of the other wavelengths. So normally, if M is small, if you go with the thin ones, the real thin ones, you're not going to have that issue because they're going to be targeted so that they're only either destructively or constructively, depending on which one you're trying to do. They're only doing that for the one wavelength. But if they get thicker, then they can do it to more. All right, so this is kind of the process, and this is how it goes. Now, think about the colors on the bubble, because I think most of us have experienced that with a soap bubble. When you're washing dishes, taking a bath, playing with bubbles as a kid. You notice how those bubbles get all like swirly and and the colors change, right?
For
Where
sure.
like you're looking at one part and it looks kind of green, and then next thing you know, it looks kind of yellow, and then maybe it goes to a reddish pink, or you know what I mean? Why do you think that's happening?
Gravity.
What's gravity doing?
It's moving the soapy molecules in the bubble. And so when the light hits it, it's going to change wavelength that you see.
Okay. Kind of. Here's how I think about it. Why, when you look at the bubble, why does it look blue, let's say? In terms of interference, why does a portion of the bubble look blue?
Because it's being constructively interfered with to look blue.
Okay, so the blue wavelength, right, whatever that is, 475, 500 nanometers, something like that, right? That is being constructively interfered. So it looks blue. Okay, but then next thing you know, it starts looking green. Okay, so why green? Well, now green is the one that's being constructively interfered. And if we kind of think about what we were doing here, when we've got an air bubble or a soap bubble, you've got air, soap, air. And it's always air, soap, air. So the reflection thing doesn't change. So it's not like all of a sudden the reason it went from blue to green is because, oh, there was some phase change or something, right? So that doesn't change. The N of the soap, no, that doesn't really change either. Which means if you think about what happens here, what has to be changing is the extra distance from the light, which means the thickness is changing. And that's why you see all those different colors on the soap bubble, is those are the different portions that have different thicknesses. And Bradley, you're 100% right that what's actually causing the change is gravity, because gravity starts pulling all that soap down. So it's changing the thickness of that film, of that soap film, depending upon where you are. And as soon as that thickness changes, you see a different color. So same deal, like when you see, like after the rain and you're out in the parking lot and you see the pretty colors on the kind of the oily stuff. Okay, so that's a film of oil that's on top of the water. And the reason you're seeing different colors is the oil has different thickness in the different places. So color is really a measure of thickness for these films. Kind of crazy. All right, well, let me show you another example using interference, but this is one that actually has practical use. And here's what our setup's going to be. We're going to have a couple of glass slides. That come together on one end. And on the other end, what we're going to have is just one strand of hair. Okay, so it's just a hair follicle that we're going to put between those two glass slides. And what we're going to do is we're going to shine a light down on this glass, and there's going to be an interference pattern that's created. And we're going to look at the interference of these two rays. The one that's bouncing off of the backside of the first glass slide, and then the one that's reflecting off the top of the other glass slide. Yes, again, there are lots of other ones that are in there, but these are the ones that are going to create the pattern that we want to see. Okay. And I'm going to tell you the thickness of this hair. Let's say that this is 0.02 millimeters. From here to here. I'm also going to tell you that this glass slide is 10 centimeters across. And here's what I want to know. I want to know, well, because here, what we're going to see actually, if we're looking down at this, is we're going to see bright spots, dark spots, bright spots, dark spots. And they're going to alternate. Because the distance, the extra distance that this light is traveling is changing. And so sometimes it's going to lead to constructive interference, sometimes it's going to be destructive. So if you were to actually be looking at this, say through a microscope, you would see lines. You'd see a dark line, then we get bright, and then another dark line, then you get bright, another dark line, and so on. So here's my question then, is how far apart are the dark lines? Okay, well, I obviously haven't given you enough information. Just like with the last one, you should all be yelling at me, what are the ends? What are the ends? What are the ends? Right? So we're going to go with that we're in air. So that's going to be n equal 1, and that's n equal 1. And then these two are glass, so we'll go ahead and use the same 1.52s. So we know we need to know the ends. But there's actually one other thing I haven't told you that we need to know. What else is missing here?
Wavelength. What are we trying to cancel out?
Yeah, we need to know what the wavelength of the light is. Right? Without the wavelength of the light, we can't figure out the wavelength of the materials and then, set that equal to 2 times t or whatever, right? So we need to know wavelength as well. Now, I'm going to help us out with this one. Instead of shining just a regular old light that's made up of all kinds of wavelengths, we are going to shine a monochromatic ray. So again, remember monochromatic, one color means one wavelength. And so this one, we're going to go with the wavelength. Let's go with the same wavelength of 550 nanometers. So we're shining kind of a greenish yellow light onto this. All right. So let's just start here. We need dark lines. So dark lines means, again, we need destructive interference, which means these two rays, when they come out, have to be out of phase by half of a wavelength. All right, so let's start with the reflections. So for these reflections, this first one, it's reflecting from glass to air. So what kind of phase difference does that give us?
Half a wavelength.
Are you sure about that? And of course, as soon as I ask that question, you go, oh shit, I screwed up.
Yes, I'm sure about it.
Well, you shouldn't be. From glass to air, there's actually no change. Because we're going from bigger n to smaller n. And when we go from bigger n to smaller n, there is no phase change due to reflection. Right, remember we're looking at the second surface, not the very beginning one. So then when we look at this other reflection, we're going from air to glass. So smaller n to bigger n, which means there is a lambda over 2 phase difference on that one. So this scenario is such that the two that we're looking at are already out of phase. So that means for us to get destructive interference, to get dark lines, we're going to need the extra distance traveled, 2t. It's going to have to equal a whole number of wavelengths this time.
For the second ray, aren't we going from glass to air?
So the first ray, this one right here, we're in glass and we're reflecting on a surface going into air, right? Glass to air. So that's why there's none. This one, we're in air going to glass. Let me, hold on a second. Here's one of those glass slides. Here's the other one. So we're like this. Glass, air, glass. And we're looking at the ones that are reflecting off of the bottom of this glass. That's the first one. And the second one's hitting the top of the second glass. So if you think that one on the bottom, we were in air coming into glass. So smaller n to bigger n. That reflection leads to the phase change. The other one, we're inside of the glass, coming back out into the air. So we're going from bigger n to smaller n. And that's why there's no reflection. Did I answer that okay for you, Bradley?
I'm sorry, I didn't hear what you said. Once you put the papers down, my internet connection went unstable.
Okay. No, I just said, does that make sense? Did I answer
Yeah, that makes sense. I guess I'm just looking at the end of the ray where it's hitting the glass again and then going out to the air.
Okay. So these, remember that they're not reflecting.
Yeah.
Those are just passing through, and we don't have the phase change when we pass through.
Yeah.
It's only on reflections.
Got it. Okay.
Okay. So the key is going to be looking at where do the reflections happen.
Okay.
Because all these other times that we're passing through surfaces, I don't care. It's only at the reflections do we worry about that. Okay, so since those things are out of phase by half a wavelength, that means that the extra distance traveled needs to be a multiple of lambda, right? And that extra distance traveled, again, I exaggerated. Remember, these are supposed to be more vertical, but that's basically that right there. And that thickness is going to change. That extra distance is going to change depending upon where we are, right? The closer we get out here to this hair follicle, the greater T is, and the closer we get to where the plates come together, the smaller it is. So that T isn't constant. But whatever that T is, it does have to equal some multiple of the wavelength. Okay, so from this, we know that the thickness then is going to be m lambda over 2. All right, now technically, I should probably go ahead and put a n on those wavelengths because it's the wavelength in that medium. But if we look at where this extra distance traveled is, it's in the space between the glass. So what medium is between the glass? What material is? Yeah, it's just air, which means that lambda is the same lambda. So we don't actually have to adjust that. Yes, the wavelength changes when we're in the glass, but it's the extra distance traveled between the glass that is driving this. So we're going to be able to use just the same old before. All right, so remember what we're trying to do is figure out how far apart the dark lines are. So let's say that this is one of the dark lines, or where one of the dark lines happens. there's going to be another place where there's a dark line that happens. Let's say that's here. And then there's going to be another place where a dark line happens, and so on, where those thicknesses are such that we're getting the right multiples. Those are for the different m's, right? But basically, I'm going to need to know how, like, what is our horizontal separation? So here's what we're going to do. I'm going to draw another picture here, just because we're getting a little bit cluttered. It looks like this. So here is our thickness. And we're just going to go with x is the distance away of that thickness. So basically, we can calculate the x for this one, or the next one, or the one before, or whatever. So the separation is going to be the change in those x's. So really, I want to find x. Well, I can get x if I know t, because if we just say that this is theta, we know the tangent of theta is equal to t over x. Right? But we can even get away from using the tangent if we think about similar triangles. Right? This orange triangle is actually similar to that. And if we use those same ratios, we see the horizontal length is 10 centimeters. So I'm going to go ahead and convert that to meters, so 0.1 meters. And then the thickness is the 0.02 millimeters. Which is going to be 2 times 10 to the minus 5 meters. Right, because 2 millimeters would be 2 times 10 to the minus 3, and then we move the decimal 2 more spots. But I can solve this for t as well. So it's 2 times t to the minus 4 times x. And I can replace that into this formula over here. So we end up with 2 times 10 to the minus 4 times x equals m lambda over 2, which then is pretty easy to solve for x. It's going to be m times lambda times 1 times 10 to the minus 4, or plus 4, sorry. No. How about over 4? Right, dividing by the 2 gives me a 4. Dividing by 10 to the minus 4 is the same as multiplying by 10 to the plus 4. So let's put in our lambda. We have 550 nanometers. So we get x is equal to m times 550 times 10 to the minus 9 times 1 times 10 to the 4th over 4. And that ends up being 125. No, a little bit more than 125. 1.3. My brain's not working. I think it's around 1.4 times 10 to the minus 5. Check my numbers on that. And then again, that's times m. So what this means, remember what m is, just like counting numbers. So when m is 0, we get x is 0, which means there's a dark spot right here. we go over 1.4 times 10 to the minus 5 meters, we're going to get another dark spot. And then another 1.4 times 10 to the minus 5, and then another 1.4, and another 1.4, and another 1.4. So the separation, remember the question was how far apart are those lines? Well, how far apart they are was this number, 1.4 times 10 to the minus 5 meters. So we can just measure each of those things, measure the distance, and it's going to be off by this. So that's is that 0.014 millimeters, I think. I don't know. It is whatever it is. All right. So believe it or not, people use this. Forensic scientists use this to help determine what kind of like hairs and threads and things they find at crime scenes. Because it ends up being a little bit easier to measure the number of dark spots. Like the individual dark spot distance might be tough, but you might be able to go, hey, in this entire length, I see 18 dark spots. You can divide your length by 18 and get however far the individual ones are. And then you can go the other direction to figure out what the thickness is of that fiber. Right. So interference is actually used in real situations, not just to be all like, ooh, look at the pretty colors on the bulb. But they're really coming from the same place. All right, anyway.
These dark spots aren't equidistant, correct?
Do you say they aren't or are?
Are not.
They are.
They are? Okay.
They are. Because remember, this M was just a counting number.
Yeah.
So you let 0, 1, 2, 3, 4, 5. It's all multiples of this distance.
Okay.
So they are equidistant.
That's kind of cool.
It's very cool. Yeah, and because of the symmetry on these things, like if you have, say, like a circular plate kind of deal. So think about like a lens, a glass lens that's curved like a bowl. If you were to put this on and do kind of the same thing, you would actually get rings, dark rings formed because of that. And yeah, no, I agree. It is very cool. But think about what we have to take into account whenever you do one of these thin film things. 3 things you got to take care of, right? 1, what's going on with the reflections? Do we already get a phase change because of it or not? Second, we got to look at that extra distance traveled, and we got to make sure that that's equal to either a whole number of wavelengths or whole plus a half number of wavelengths, depending upon which of the scenarios we're in. And then make sure that the wavelength in the material has been adjusted due to the n value in the material. Okay, so it's all of these things get wrapped up into one. But as long as you follow those processes, you're going to be good to go. Real quick before we move off of this one, what if this had been in, say, water? So there was water in between the slides. What would change?
The thickness.
Thickness, yeah.
The thickness actually wouldn't have changed. Not likely. Unless the water is causing it to like push up or something. But like if instead this was just filled with water, but the thickness was still due to the hair follicle, the thickness wouldn't change.
The X would change, or distance apart would change, because the n value is different than air, but it's not greater than the glass. Okay,
so as soon as there's water in there, we go, okay, so that's like 1.33, let's say. That's going to change our wavelength in that extra distance. And so this we would have to, it'd be off by that factor for water, for 1.33 or whatever. So that would change. What about the reflections? Is there a change there in terms of the phase differences? Think about the first one. We're going from 1.52 to 1.33. So we're going from bigger to smaller, just like here. So you would see exactly the same thing. And then for the second one, we're going from 1.33 to 1.52, from smaller to bigger. So we'd see exactly the same thing. So if you were to fill this with water, you don't have to worry about differences in reflection. That didn't change. The only thing that's going to change is your wavelength in between the two glass. But it's possible that if we were to change things so that, okay, there's water inside and then ice in one of the two, ice is N is 1.3. So like if it was two slabs of ice with water in between them, well, then we have all kinds of new things we have to worry about. Right. So just realize that this one example, I point this out because a lot of times people will go back and they'll look at their notes and they go, oh, here's an example for something between, a little wedge of things. I'm just going to use this example. And you get screwed because you don't realize that, oh, no, this example was glass to glass. That other one's got ice in between. Next thing you know, things are wonky, right? So just go through the steps, right? Look at the reflections. Look at that extra distance and make sure in that extra distance you've accounted for different wavelengths. All right, so interference. It actually shows you why a lot of the things that we see out there exist, but there are also some of those funky things, like the fact that the double slit makes it so that we get alternating bright and dark spots. So I have a question because I wasn't there with you guys last week in the lab. Did you guys also look at single slit patterns?
Yeah, we did single and double.
Okay, so what did you see with single slits?
The bright spots were larger than the dark spot.
Okay, so you still had bright and dark spots, but the bright spots were brighter, or you said larger, Victor, do you mean wider?
Yeah.
Or brighter, more intense?
Both, I guess.
Maybe both, but definitely thicker. It looks like Ralph's backing you up on that too. Okay, well, here's what's kind of weird is that, like, we explained why you should see that pattern with two slits. It makes total sense with the wave idea, right? Why are you still seeing that with one slit? Right? Because if we've got a single slit, here's our single slit here, and we think, like Huygens, for instance, well, okay, so we got a wave that's just coming out of this. Why is there interference happening? The double slit, it was because there was another slit down here that was creating another wave front that was canceling itself out. So what the hell? Why was that still happening? I don't know. Did you guys think about that? It's okay if the answer is no, but
It was 8 in the morning.
It's because of diffraction.
There wasn't a lot of thinking going on because it was 8 in the morning.
Yeah.
Okay, well, because it's not 8 in the morning now, and we're kind of thinking about it. That seems wrong, right? you shouldn't have seen that pattern. Even if you go with the, well, okay, well, maybe we'll see brighter in the center and then it'll get darker as we go further away because it's a greater distance and we're losing intensity of light and it's a field and blah, 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 blah. Right? Like, I mean, that at least would make sense. That it should get dimmer the further you go on either side because it's traveling further. But the really bright, really dark, really bright, really dark should not have happened. Okay, well, have no fear. Bruce is going to show you why that still happened. So think about this opening. We're not going to think of it as a point. We're going to think of it as a whole bunch of points that are spread out. But specifically, let's look, say, at the wave that's going to be created at the very edge of the slit and the one that's going to be created in the middle. So I know that there are other bits of light here. Yes, I know there are, but let's just think about those 2 points for a second. So they're going to do what they do, right? They're going to send out, there's the semicircles coming from the first one, or the one in the middle, and then the one up top is going to do the same thing. And we recognize that there are places of constructive interference. Right? So these are places where it's constructive. And there are places of destructive interference. So there's a few of them. And we do recognize that they're going to go destructive, constructive, destructive, constructive. So those two are going to lead to a bright, dark, bright, dark, bright, dark kind of pattern. Okay, well, if we still follow the sort of, well, where are these going to occur kind of things, if we were to send those out here somewhere onto a screen, we do the same thing about the difference in distance deal. Remember when we did that and we look at this little extra chunk? That extra chunk from the trig, so the extra distance, it's going to equal a over 2 times the sine of theta. The A is the width of the slit. So the A over 2 is the hypotenuse side here. And then theta is the angle, the top angle in there, which is also the same as that angle. Right? So it's exactly the same derivation that we did before for 2 slits. It's just there, it was the distance in the 2 slits. All right, well, again, for this to end up canceling out, let's say that this is a dark spot. For the dark spot, this is going to have to equal half of a wavelength. So from that, we get sine of theta is equal to lambda over A. Using the small angle approximation, if we say that, again, the screen is a distance of L away and our spot is X up, that sine is the same as the tangent, which is the same as theta, the small angle. So you get X over L equals lambda over A, or X is equal to L times lambda over A. So we should see a dark spot there from those two. Okay, but now I know what you're thinking. Well, you're probably thinking at 6 o'clock, you said we were gonna go. Well, let me finish this real quick. But you're probably also thinking, right, but there's a whole bunch of other points here. other points of light. Well, what if we take this one and this one that are also separated by half of the width? And we take another pair that are separated by half of the width. And we just keep doing that. So we're going to look at this one and this one, and this guy and this guy. Right? We can pair them up so that every pair is exactly half of a wave or half of the distance apart. They're all going to do exactly the same thing, and they're all going to cancel each other out. So at this spot, we're going to get dark because every pair, you're able to split it into groups of two that cancel. Okay, well, choosing to just cut it in half was kind of random. What if I cut it into fourths or sixths or eighths or sixteenths or so on and so forth? Well, what's going to change there? Let's say it was in fourths. This is now a 4, which makes this a 2. So there would follow through that there would be a 2 here. If we cut it into sixths, this is a 6, which makes it a 3 over here. Eighths, it's a 4 over here, and so on. And so if instead of just randomly deciding to cut it into 2, we cut it into fourths and sixths and eighths and so on, it turns out that we start getting dark spots at multiples of this L lambda over A. So the dark spots are going to happen regularly. And that's what you saw when you did the single slit experiment in lab. You still saw that there were dark spots that occurred regularly. And that's why. So it's kind of trippy that just one slit is going to do this. Now, we're not even by any stretch of the imagination close to being done talking about this, because if you think back to what you saw those bright and dark spots, but hopefully you also saw that the brightness of the bright spots changed depending on where you were.
Yeah, it
Well,
got dimmer as you went farther away from the quote unquote center.
Yeah. And what's even crazier, I don't know if you remember this, but it was like super bright in the middle, got dimmer, and then got brighter again. Not as bright as the middle, but got brighter, then got dimmer, then got a little brighter, and then got dimmer. And so there's some weird variation in the brightness, but we still need to talk about why that happened. But this is why a single slit still shows that interference. Now, I'm going to tell you about a great way that you can actually see this without any kind of technology. All you need are your 2 fingers. If you put your fingers really, really close together, right, you're creating a single slit for light, right? You see the gap there between my finger. Okay, now if you hold this up to your eye, you got your fingers really close together. I mean, there has to be a gap. You see the gap there, right? A little tiny gap. You hold this up against your eye and you look at a light source. Don't do a super bright one. You don't need super bright. What you're going to see, you bring your finger, kind of push your fingers closer and closer together, you'll start seeing a bunch of black lines in between the space in between your fingers. Now, this can take some practice to actually be able to see this. All right, but you do this, you'll start seeing black lines. And what you're seeing is this single slit interference. Single slit, right? There's one little gap. When you see those little black lines, those are your dark spots due to destructive interference. All right, so practice on that a little bit, see if you can actually see it. But it's pretty trippy. You kind of got to bring your fingers close to each other where it's almost like there's no gap. But you'll see a series of parallel black lines between your fingers. So you can actually see single slit interference just using your body. This annoys the hell out of my wife. Not that this happens, but because I am so like obsessed with it. I'll be like, we'll be like lying in bed. She's reading a book or something. The lights are still on, and I'm just, getting ready. And I'll just stick my fingers up, looking at the light. Like, and she'll turn to me and is like, "Would you knock that shit off?" I know about interference. I'm like, right, but it's so damn cool. So now I do it just to mess with her. That's kind of fun. But anyway. Okay, so what we'll do on Tuesday is we'll pick up where we left off, and we'll look at, okay, so what about the intensity on this? And then we'll kind of put this together with double slit, because when you did the double slit experiment, you actually saw both of these things happening, because each of those slits was doing single slit interference on top of double slit interference. And hopefully you remember it well enough, you remember what you saw, that when we talk about combining them, you'll go, oh yeah, okay, so that's exactly why we saw what we saw. Anyway, so we'll talk more about this, and then we'll talk a bit about, it's called diffraction. Actually, what we're talking about right now is diffraction. But we'll talk about uses of it, why we care about it, like the fact that it's part of your literally everyday life, in probably multiple ways that you don't realize. Anyway, we'll talk about that later. Okay, so I think with that, we're going to go ahead and call it a day. So I'm going to wish you guys all a wonderful weekend, and hopefully 8 o'clock lab tomorrow is not so horrible. All right. So have a good night, everybody.